So today's job should be pretty interesting. I need to extract node dates from this time calibrated backbone tree. Normally I don't really work with node dating very much, just because to get a good topology is a huge challenge in itself. But I need to do this for the current project. So I'm just having a quick look. So this is a published or soon to be published omics backbone tree for bees, and this has been time calibrated. So just what I need to do is just pull out the dates, and I'll use these dates as calibration points in a synthesis tree. So just taking a quick look at the subject for today. Now it's ultrametrics, so we have having a look at these two species, Euglossa lugubrious, Euglossa phyloventrus. So the branch from this terminal to the most recent common ancestor, well, the most recent common ancestor of these two terminals, because it's ultrametric, these will be the same. You can see these are the same length of branch, both 7.58. Now, so we're pulling out the most recent common ancestors, so I've just called the script MRCA dates. So we're pulling out the MRCA dates. So for the MRCAs for the terminals, pretty easy, just pick one of these dates. Now as we parse the topology, we'll be getting through all the internal nodes. So the main thing to be doing as we pull out a bifurcation, we will need to just pull out one of these dates for the MRCA, and then we need to add that length to this length here, which is a length from the MRCA to the next node, so this length here. So that will give us a sum for this length, and that will be the new length for that node which has been pulled out. And then just repeat that process for all until you've got nothing left in the string. Okay, so I think that's what needs to be done. We'll see if it goes so smoothly or not. I think I'll try a brand new script for this, because I've not really done this, not really worked with lengths, branch lengths and dates before, so I'll just it's probably not so much which will be helpful. So I'll just start a new script to parse this nuke string. So let's name of the script mrca dates.pl. Here's the file name that we've just, here's the contents here. Nothing in the script right now, and let's get going. So we've written this nuke string, put it into a variable named tree, and we're pulling out strings which start with a open bracket, then have a set of characters including letters and underscores, which will be the node ID. Then we have a colon, which denotes the start of a branch length. Then we have a series of characters including a number and a dot, which is a branch length, and we have a comma, which separates the child nodes of a node, the descendants of a node, or the child nodes of a split. Another word, another colon, another branch length. Then we have a closed bracket denoting the end of the specified bifurcation. Then we have a colon and the number, which is the length of the branch adjoining those on the way back to the root. So for instance, I've put it into a while loop, but just terminated it after a single iteration, and the output is here. So we have child1 node ID, terminal name, and this, as the string gets pulled out, this will include internal nodes, branch length, child2 node ID, branch length of that, which should be the same for, at least for the terminals, and then the adjoining branch length. So this just, I mean, I could write this into I was thinking how to do this. I could write this into a replacement here, but I think as we need to perform a calculation to add the branch lengths, I might need to do the calculation and then do the replacement to include the modified branch length and the new node ID. So we'll start a variable with the node IDs. And we'll try replacement. So we'll do a calculation here which adds the branch lengths. And then we'll do the replacement regular expression here, which will look very similar to this with a minor change. So replacement regular expression. So this is just matching, not doing anything other than pulling out the details. But here we're going to replace the match with something. And as long as we have the identical regular expression, then it will pull out. It will match the same thing. So S for replacement. And then for replacement we'll have two of these, two sets of /, first making a match and second for replacement. So here we need to figure out what to replace with. So I might put IN for internal node, then have a number, which means the number needs incrementing, and then we need a new branch length, which is here. So we're replacing all of this here with a new node ID, internal node, which we've created ourselves, and the new branch length, which is this plus this. So let's try this. So we start off pulling out terminals, or the node, the splits just next to terminals. You see the typical terminal IDs on here and here, and then we're transitioning into internal nodes as we get down, and eventually there should be nothing left. We should print that out. assumed this is fully bifurcating, but maybe it's not. 3 Serratina species for a single, going to a single MRCA. So there are multiplications, and so I'm a bit surprised for an omics tree. Usually, always really well resolved. We might detect this by, though there'll be quite a long string here, as it's not all been parsed. So we'll just specify if it's quite a long string, say 30, then terminate with error message. Okay, so if it's run on a tree with multiplications, then it's not gonna run. So I'll now open this backbone and remove these. So click on Node Data to scroll down a bit, and you can see here delete subtree node. Let's find these pesky multiplications, and here's one. So I'll just delete this. Save as Newark or New Hampshire, and try this again. Okay, just confused myself for a moment. So now we've got a fully bifurcating tree, and we've pulled out all the nodes except for we can ignore the root here. So this gives us the lengths at each, or the times at each internal node. Now what we need to do next is to determine what are the descendants. We need to specify the date of a most recent common ancestor according to two descendants. So we need to somehow determine what are the descendants. Okay, so I've come with a very simple solution to this. So actually I just inserted a single line, and so again we calculated the branch length. So for a given, say if it's for simplicity, if it's terminal, then you have the most recent common ancestor will just be the length of directly for the child. So just put the child on branch length, and I've specified this as child 1 node ID, child 2 node ID. And instead of making new node IDs as we move into the tree, I've just replaced that bifurcation with a single node and taking one terminal ID at random. Now this might not be optimal in the current application, because there'll be a few maybe partial overlap between the backbone and the synthesis tree. So ideally we would select an overlapping one, but we're just putting one at random. But this is very simple, so we're just replacing the bifurcation with one of the terminals at random. So we're keeping terminal IDs, and then as we go into the tree, we're specifying most recent common ancestors for those accordingly. Just really, we should have a check. I don't think it should happen, but if this has been specified already, then we're going to have a problem. But I don't think that should happen. But we should have, always good to have checks. Yep, so that shouldn't happen. Okay, so specifying most recent common ancestors for descendants randomly. So if we have a given split, one is randomly selected from one of the child nodes, descendants of a child node, and another terminal descended from randomly selected from the other split, and updating the branch lengths accordingly here. And then, so it gives us a bunch of keys for the terminals put into this array, then looping through and getting a date. So when we do this, we get most recent common ancestor of terminal 1, terminal 2 is dated at this. So let's check some of these dates. So if we click on a node in our Archaeopteryx, it gives us distance to root 124. Unfortunately, it doesn't give us a distance to the tip, but we can calculate that from subtracting from 124. So let's just pick one of these at random. Okay, so we've got these two first. Most recent common ancestor of these two species is here. Click on this node. Date will be 124 minus this value, 110, 14. So the date should be 14, and yes it is. Good. Choose some much deeper value. Okay. So the most recent common ancestor of these two will be this node here. So 124 minus 68.6 equals 55.4, and the vote. Okay, my highlights disappeared again. Which one was it? This one. 55.5, 55. Yep, close enough. On the top of the time calibrated backbone. Most recent common ancestor of these two will be this node, and 124 minus 57.2 equals 66.8, which is what we have, yes. So this is working fine. Okay, so I think that's job done. We have read in a time calibrated backbone, which is this one here. Read in a nuix string, put it into an object called tree, put it into an object called tree. Parsed the numeric string, pulling out each split, replacing it with one of the child IDs, and recalculating the length, adding the lengths as we go into the tree. Putting these into a hash MRCA's most recent common ancestors for each node, and the branch the length of the branch to the tip. Putting these into an array and then printing out all these. This is done. What I need to do next is I'll just change this into the format for TreePL, which is pretty similar. I just need to check. I'll check that these are in the synthesis tree. So each of these, which both of these terminals is in the synthesis tree, this can be a calibration point for the synthesis. And job done. So until next time.